All right, here we go. We're starting the unit on acids and bases. And if you recall from Unit 3, we did discuss acids and bases back then in kind of a rudimentary fashion, right? Just kind of definitions and the elementary reactions that take place. Obviously, we're going to go deeper than that here. So let's start off with some properties. So first of all, acids and bases are generally clear, which means they look the same, right? Acids have a sour taste to them. Bases taste bitter, right? So sour, think like citric acid, think like limes, lemons, right? Things that make you pucker, right? Vinegar. As far as bitter tastes are like, really, really dark chocolate, right? Things that you feel like you need to add sugar to, right? That's like the bitter taste for bases, okay? Acids will corrode metals, right? And depending on which metal is, some corrode much more easily than others. And we'll go through all the hows and whys later on. That's actually in our next unit. They turn litmus red. So you've heard of litmus paper, right? Litmus paper, it's what we call an indicator. And indicators change colors when things are acidic or basic. So litmus is an indicator, and if you dip litmus into an acid, it turns red. Acids will burn if touched. So depending on the concentration, in sophomore chemistry, the concentrations that we used were not really strong enough for you to notice if you got acid on your skin, right? Because they're generally 0.1 molar or less back then. We have been using acids of much higher concentrations. And has anybody gotten any on your skin yet this year? Do you feel it right away?
Yeah, literally.
Okay. So acids, your skin, when you have dry skin, you don't notice it, but there's microfractures in your epidermal layer, and then the acid seeps through that top layer quickly, and then you notice it, you feel it faster if you have dry skin, right? If your skin is decently hydrated, decently moisturized, then your barrier is more intact, and you probably don't feel the acid right away, right? And in wintertime is when you would have the driest skin, right? Whereas the summer, you're always sweating, the humidity is higher, right? You're more likely to not be dry. So in any event, they burn. Acids are electrolytes. Remember, electrolytes allow for conductivity in solution. Bases have the bitter taste. Now, bases feel slippery, right? So slippery like when you're washing dishes and using detergent, slippery, right? So if you've gotten ammonia or sodium hydroxide on your fingers during lab, and you feel like, oh, this is really slick, really slippery, well, that's because you had contact with a base. They turn litmus blue, right? Blue for bases. Okay. Well, if I could spell the word blue. Okay. And bases are electrolytes as well. Why are bases electrolytes? Because of this. That's an ion. Why are acids electrolytes? Because of this. All right. Let's go through definitions. We talked about some of these definitions, at least the first two back in Unit 3, but we're adding a new definition now. So first one is review. The Arrhenius definition says that acids produce hydrogen ions in solution. Bases produce hydroxide ions in solution, right? Hydrogen ions, hydroxide ions. But here's the thing you got to remember. Hydrogen ions do not exist in isolation, right? They bind to water. They bind to water and form the H3O plus ion, which has a name. It's called hydronium. And this is always the case in aqueous solution. If there's an acid present, it's actually in the form of H3O plus. Okay? So when you see things like problems where they mention the H plus concentration, right? If they mention H plus aqueous, right? Really, at the end of the day, what's really happening is it's H3O plus. Okay? All right, so that's the Arrhenius definition. Acids make H plus, bases make OH minus. The Bronsted definition, or Bronsted-Lowry, right? But Bronsted is shorter. The Bronsted definition says that acids are proton donors. Bases are proton acceptors. All right? And the advantage to defining things by the Bronsted definition is that you are not limited to aqueous solutions now. Now you can have this take place in non-aqueous environments, right? So that's a limitation of the Arrhenius. This is limited to water solutions, right? Because the definition says H plus in solution, right? Okay, so in a Bronsted, according to the Bronsted definition, you will have an acid and a base present. The exchange will happen between them. So here, if I kind of highlight, here's a hydrogen ion, right? That begins in the formula HB. HB is just a generic acid formula. You'll see this a lot. HB. Sometimes you might see it as HA. Sometimes you might see it as HX. It doesn't really matter what the letter is. It's H in front of something. Okay. So here we have HB, and it is in the context of water, and the H is transferred to water. And what happens is the HB is no longer HB. Now it's just B minus. Right? So there's terms for these. If you can identify which formula gave up the H plus, then you know that that is the acid. Right? So the proton donor was HB. The acceptor must have been water, because water gained an H plus in order to become hydronium. So the other concept is that whenever there's an exchange, the resultant is a base and an acid, but we call them conjugates. So if I just connect the two things that look most alike, if HB is the acid, then what we end up forming from that formula, B minus, that is what's known as the conjugate base. Right? If water behaves as the base, then H3O plus is the conjugate acid. So in other words, conjugates are the same formula that differ by an H plus. Okay? Here's some other examples of conjugates. HF and F minus, those are conjugates. HSO4 minus and SO4 minus 2, those are conjugates. In each one of those cases, the only difference between them is an H plus. And because an H plus is being transferred, your charge must change. Right? So be wary of that. That's an easy thing to overlook. Okay? Anything that gives up an H plus, its charge is changing. Anything that gains an H plus, its charge is changing. Okay? Now, I should point out, you see here water. We've decided that water is a base in this example. Guys, of course you know water by itself is not really considered a base. The reason why it's a base here is because in this context, water is the only thing that can be a base. Right? So when we're talking about Bronsted-Lowry acid-base reactions, there's got to be an acid. There's got to be a base. Right? Whichever one is better at being the acid is going to be the acid. Does that make sense? Okay, even if I put two acids together, if one of them ends up donating H plus, one of the other one's going to be the base just by default. Okay, so the acid is not so literal when you're considering the context of one equation. Okay. Okay, so new term, amphoteric. This is when a substance can behave both as an acid and a base. What do I mean by behave as an acid and base? I mean that it can either donate or receive a proton. Right? Water is the most common amphoteric substance. H2O plus H2O. Actually, you know what? I'm going to rewrite it this way. Let's write it in acid-friendly language. HOH plus HOH will form on its own H3O plus and OH minus. Right? What happened here? Well, one of these was donated, right? And so the result is this guy, HOH, the first one, started out as an acid, and then it became the conjugate base. HOH, the second water, this acted as the base, but now here it's the conjugate acid. So make sure that you can evaluate an acid-base reaction and properly identify what's what. Okay, so another example, bicarbonates. Bicarbonate is HCO3 minus. Paige, remember our big acid spill of 6 molar HCl on the counter? What did I cover that with? Baking soda. Yeah. Baking soda is sodium bicarbonate, right? And I keep boxes of that on hand because it can neutralize an acid and a base. Like, I don't want to be stopping and thinking, oh, which one should I grab? Just grab the baking soda. It will neutralize both. Here's how it does that. So, in the presence of an acid, the baking soda, the bicarbonate, will absorb the H+. And then the result is, well, it's H2CO3, which actually becomes this because it converts to a gas. Remember that? Remember carbonate reactions with acids, guys? Unit 3? Okay. What about if there was a base spilled instead? Well, then I would take my bicarbonate, and the bicarbonate would be the proton donor. So it would act as the acid, and we would end up forming H. It's the conjugate. Whoops. No. Conjugate acid. Sorry. Conjugate acid. Conjugate base. It would end up absorbing the H plus and neutralizing the acid. I'm sorry, if it's acting as the acid, it donates its H plus. The point is, either the acid or the base is neutralized, right? Bicarbonate will do that. Bicarbonate does this much better than water, so we can't like neutralize an acid by throwing water on it, right? But bicarbonate is it's like perfectly suited to do this. Okay, here's another example. Take a look at this formula. Bisulfate. Technically, bisulfates can give away a proton because it has one. You guys see that? But it can also absorb a proton, right? Because it's negatively charged. Ions that are negatively charged have a tendency to attract protons. So technically, this would be able to act as a buffer as well. It's not a very good one, but just by definition. The best ones are bicarbonate by far, right? When in doubt, if you need to neutralize anything and you want to keep things safe, bicarbonate's a nice one to use. Okay. Acid formulas. We talked about how you can identify an acid because the H is deliberately placed in the front of the formula. HCl, HBr, HI, HNO3, right? These are what we call monoprotic because they only have one hydrogen that is acidic. Only one hydrogen that can be donated. You could have a diprotic acid, in which case you will have 2 acidic hydrogens placed in the front of the formula. H2SO4, H2S, and so on. You could have polyprotic, something like phosphoric acid, which is H3PO4, right? 3 acidic hydrogens that it can donate, right? We don't really see anything greater than that, okay? So polyprotic, sometimes it's just called triprotic because there's literally 3, tri for 3. All right. If you read any kind of lab instructions and it says such and such as a monoprotic acid or a diprotic acid, you need to take that into account because you need to realize that there's 2 hydrogens that can come off, or only 1. Okay? All right. Remember the concept of strong acids? Remember how we said a strong acid dissociates completely? I think I have a list here. Okay, we'll jump down here real quick. Here's your list of your common strong acids. Perchloric, chloric, hydrochloric, hydrobromic, hydriodic, nitric, sulfuric, right? These guys, once you mix aqueous solutions of them, they will separate 100%. Okay? There's only, well, in the context of what you will see, there's only 7 strong acids that you need to know. But what if the acid does not separate completely? Well, if that's the case, then we have what's called a weak acid. So, weak acids. For example, hydrogen fluoride. Hydrogen fluoride, you might think it belongs on the list of strong acids because it's in the same family as chlorine, bromine, and iodine, right? But it is not a strong acid. This dissociation does occur, but it does so with equilibrium. All right? So, if I compare a bunch of acids here, I've got HCN, HF, HCl. HCl we know is a strong acid. All right? And so that means if I have a 1 molar solution of HCl, I will have 1 molar of H+. Does that make sense? All of it dissociates. But if I have a weak acid like this, HF, all right, this, guys, has equilibrium. And anything that has equilibrium, you can apply the law of mass action to. Right? Products over reactants. And that's a numerical value for the Ka. In this case here, it's told to us to be 7.2 times 10 to the minus 4. So imagine if I said, all right, let's find the concentration of H+. All right, let's say that we have a 1 molar solution. 1 molar, 0, 0, plus x, minus x, 1 minus x. So I've got x squared over 1 minus x. Okay, let's find out what our concentration of H+ is. Yes?
Do we just ignore the x, possibly? At the bottom?
Probably. Yeah. So 7.2 times 10 minus 4. Let's screw it. All right, so we're looking at a concentration of 0.027. We'll just round it. Okay? So 1 molar HF produces 0.027 molar H+. Well, that's not a very high conversion rate. Right? Given the size of your K value, 7.2 10 to the negative 4th, is this product favored or reactant favored? Given the magnitude of that K value. Reactant favored, right? It's less than 1. Okay, so that means if you have 1 molar solution of HF and you spill it, you know, you only have 0.027 molar H plus. Okay, now HF is actually very toxic for different reasons, but the point is it doesn't dissociate a whole lot. So you're looking at a dissociation percentage of 0.027 over 1 times 100%. So it's 2.7% ionized. Do you guys see that? This is something that you'd be asked for. Percent dissociation. It's the concentration of H plus you get at equilibrium over the concentration of the acid initial times 100%. So 0.027 over 1 times 100, 2.7%. What is it for HCl? 100%, right. Okay, so let's try this other one here, HCN. Probably could have given myself more room here. Let's just do a small ice table. Let's use 1 molar again. Again, you can ignore the subtraction of x in the denominator. So really effectively, you're just taking the square root. All right, so x is equal to 2.5 times 10 to the minus 5. So what's our percent dissociation? Well, it's going to be 2.5 times 10 to the minus 5 divided by 1 times 100, which will be 0.0025%. All right. Can you rank the acids from weakest to strongest? I think so. I don't think there's any debate here, right? They turn out that they are ranked, right? Okay. First and foremost, are you guys okay with taking a weak acid and using the Ka value provided to find the H plus? That H plus that you find is at equilibrium, okay? It's at equilibrium. So you can find out what the H plus concentration is at equilibrium just by working the equilibrium ice table. All right, so the conjugates of strong acids are the weakest. All right, conjugates of strong acids are the weakest. Okay, what does this mean? So didn't we identify HCl as a strong acid? What is the conjugate base of HCl? Yeah, Cl minus, right? So what are my conjugate bases that I have here? I've got Cl minus. What's another conjugate base here from this set? F minus. And the last one? Cn minus. I have 3 conjugate bases here. So here's the thing, all right? Chloride is the weakest base in this set. You see, the stronger something is as an acid, the more ineffective its conjugate is as a base. Okay? Weakest base since HCl is strong acid. And we'll get into the nitty-gritty and do the calculations to prove that in a little bit, okay? But maybe not today. F minus and Cn minus. Can you make a prediction? If I have F minus in a solution and I have Cn minus in a solution, which one of these 2 ions will be more basic? Cn minus, right? Because between these 2, this will be, we'll call it moderately basic and weakly basic. So the order goes base, strength. Cl minus is the weakest as a base. And then F minus, and then Cn minus. All right? Because we were able to rank the acids, right? We said that HCl was the strongest acid, therefore its conjugates would be the weakest base. F minus was in the, or HF here, and it was the middle acid, right? So, and HCN was the weakest acid. Well, the conjugate of the weakest acid is going to be the best as a base, the strongest base. And you know what? Actually, I can just show you now to prove it, just because why not? So, there's this concept. Ka times Kb equals Kw. We've mentioned Kw before. You guys remember what the value of Kw is?
10 to the negative 14.
Yes, right. So, if I know this relationship and I know a Ka, I can solve for the Kb, and vice versa. So the Kb would be the Kw over the Ka. So I can find the Kb for each one of these conjugates, but we should mention that. We have to put a little caveat on there. This is for the conjugate base, right? It's for the conjugate base of the acid. And so that's important to remember. So let's solve for the Kb of F minus. So Kb is equal to 1 times 10 to the minus 14th over the Ka of HF, and the Ka of HF was told to me to be 7.2 times 10 to the minus 14. I'm sorry, 10 to the minus 4. Okay. All right, so the Kb is 1.4 times 10 to the negative 11. And that's Kb specifically for the fluoride ion. All right, let's do this again for Cn minus. Kb is equal to 1 Kw over 6.2 times 10 to the negative 10. Oh, I misentered something. All right. These are the two Kb values. I have two basic ions here, F minus and Cn minus. The higher the K value, the more that equilibrium goes to the right. Remember, right? The more it favors the product. What product are we talking about? Well, let's take Cn, for example. What could Cn do to be a base? It would do this. These ions undergo the process of hydrolysis. Hydrolysis is, the word means splitting of water. So it reacts with water and it splits water, and the result of that is going to either be H plus or OH minus. All right, so here it takes an H plus off of water to form OH minus. What would the fluoride concentration look like? Well, what do bases do? They take protons. It would reform HF and form OH minus. So, both of these ions undergo basic reactions. The only difference is one of them is going to produce more hydroxide than the other. The one that produces more is the one with the higher Kb. Which is which? Cn minus. And that is how we justify this being the strongest base out of this lot. Okay, we went a little deeper than I was intending on going here on the first page of notes, okay, but we're going to constantly reaffirm this. We're going to constantly keep showing you this logic, right? And then it'll eventually become intuitive for you to be able to gauge weak acids and weak bases against each other. Because ultimately, while there's a lot of strong acids being used in this unit is primarily about weak acids and weak bases, because we did all that strong acid, strong base stuff back in Unit 3. All right. So that was a lot about the Bronsted and equilibrium. Let's talk about the third definition of acids and bases. This one was completely new. We've never talked about it before. The Lewis definition. In the Lewis definition of acids, acids are electron pair acceptors. Notice how the definition is not geared around H plus anymore. We're not talking about H plus or protons anymore. We're talking about electron pairs. And so something that accepts a pair of electrons, sort of like how a central ion would in a complex ion, right? That's what we call a Lewis acid. And the bases are the electron pair donors, meaning they have a pair, a lone pair to use. So Lewis bases must have at least one lone pair in order to be a Lewis base. Remember the ligands from last unit? How the ligands all had to have a lone pair in order to attach to the central ion to form a complex ion? Those are all Lewis bases. So if we look here, actually, let's talk about that one first because I just brought it up. Here's the copper 2 ion. You guys dumped a bunch of concentrated ammonia with copper solutions, and you formed the tetraamine copper. In any complex ion, the ligands are bases. They're Lewis bases. Why? They are bringing the electrons to the party. They are electron pair donors. The copper 2 plus ion is the Lewis acid. It accepts the electron pair to form a bond with ammonia. What's that bond called?
Coordinate.
Yeah, the coordinate covalent. Yes, Ron.
So, is the Lewis definition kind of like reversing what we know?
No, it's not. It's not reversing anything because the Lewis acid does not conflict with the previous two definitions because the Lewis is focusing on electron pairs. The previous two definitions are focusing on either hydronium or the proton H+.
Oh, okay.
Yeah. So they will not conflict, but there will be some cases where an acid is an acid only by one definition. There's some cases where an acid is an acid by two definitions. There's some cases where an acid is an acid according to three definitions, but they will not conflict. Okay. So this, like in this case right here, if we look at this, BF3 and NH3 to form BF3NH3, right? These are all occurring in gas phase. If this is in the gas phase, what definition does not apply? Yeah, this cannot be an Arrhenius acid. This cannot be an Arrhenius acid. This cannot be an Arrhenius base because it's not in solution. Does that make sense? Okay. Is there a proton being donated anywhere? No. So it's also not a Bronsted acid or base, but it is a Lewis acid or base. All right. Hey, look, I just redrew the thing that I already inserted a picture of here. All right, glad I noticed that. Okay. So the Lewis definition is based on electron pairs, right? It's not based on H+. Okay, so let's pause for a second. I want to give you a reaction or two, and I want you to do some identifying for me. Okay. So here we have predicts the products of this reaction. This is sulfite, SO3 minus 2. What are we going to get? Well, this unit is called acids and bases, and in order for something to be an acid, it has to do what the three definitions say it does. Can SO3 be an acid according to Arrhenius? In order to be an acid according to Arrhenius, what must you have? You need to have H+, and it doesn't have an H+. Okay? But water does, right? And so water can donate its H+. So hopefully you wrote this. SO3 2 minus is the base in this example. Water acts as the acid. And again, calling something an acid or base is a relative term. The water is the acid because the SO3 is most decidedly a base. Okay? So which one of these is my conjugate acid? Or pair these up for me. How can I pair these up? What do you think? Irina, can you match up some of these on the left to the right side?
So the SO3 minus 2 will become the HSO3 minus. So
Oh.
it becomes the conjugate acid.
Good. And then by default. Okay. All right. So strong acids, strong bases. We talked a bunch about the strong acids. Here are the strong bases again. Sodium, lithium, potassium hydroxide. What if you were presented with cesium hydroxide? Would that be considered a strong base? Yes, it would. The only difference is it's just exceedingly rare, right? You probably won't encounter it, but it would dissociate completely, and it would be a strong base. Rubidium hydroxide would also, but don't bother. You know, the alkali metals, the alkali hydroxides are all strong bases. Yes, Ron?
Would magnesium and calcium hydroxide they wouldn't be strong bases?
So the problem with calcium and magnesium hydroxides is that their solubility is very limited, and that impedes their ability to dissociate completely. So that would only be the case in relatively minute concentrations. Okay. Okay. So we've actually talked about a lot of this in a little bit out of order, right? But basically, strong acid, if you wrote a nice table for it, you would see that whatever the initial concentration of the acid would all become the concentration of H+, right? There's a nice table here, but there's no equilibrium. And there's no equilibrium, then that's how you know it's a strong acid, all right? Okay, pH calculations. We did a little bit about this before, but let's talk about it again. So the pH scale is how we measure acidity or basicity. It's a negative logarithmic scale. And so logarithmic, we're using base 10, right? I know that we've used natural log a lot in this class, but for the purposes of the number crunching here, it's base 10 for pH. So the fact that it's base 10 means that for every power of 10, the pH changes by a value of 1. But it's a negative logarithmic scale, which means the higher the concentration, the lower the pH value. So your base equation is here, and to start off, by using any H+ concentration, you should be able to find the pH. Right? So let's say the H+ concentration is 2.4 times 10 to the minus 6. Just type in the negative log of 2.4 times 10 to the minus 6, and you will get a pH. Well, you tell me, what pH do we get? Okay, that's right. 5.62 is the pH. And remember, we consider 7 to be neutral. Okay, so this is mildly acidic, right? This would not harm you, right? In fact, tap water around this area here that comes from the ground. It absorbs the carbon dioxide from the air, and that actually makes it mildly acidic. And so it actually comes out at pH about 5.5, 5.6, right? And you drink it all the time, right? You drink acids all the time, pop, coffee, apple juice, orange juice, right? So your body can tolerate those. Okay, a note about sig figs. So because the pH calculation is a logarithmic value, only figures to the right of the decimal point are regarded as sig figs. So if you are told a pH of 7.85, that 7 is a category. Think of the 7 as not a number, it's a category. And really the numbers are, the 8.5 are the sig figs you consider that you actually have. And so a pH of 7.85, we would only regard that as 2 sig figs. And if we took that and we converted it to H plus by doing the second equation here, right? So let's say I said, all right, what's the H plus concentration for this pH 7.85? To find that, the opposite operation is H plus raised to times is equal to 10 raised to the negative pH value. So 10 raised to the negative 7.85 would yield 1.412537545 times 10 to the minus 8th molar, but because the pH value only had 2 decimal values, your expression of concentration would be 1.4 times 10 to the minus 8th molar. Guys, does that make sense? On a pH scale, the number to the left of the decimal is not a number. It's a category. Okay? It's a power, right? All right. Tell me what the H plus is if we have a pH of 8.68. With sig figs, what would it be? What do we get? Bethany, what did you get for H plus?
2.1 times 10 to the negative 9.
Right. Okay. So, be able to solve for pH, be able to solve for H plus. Now, as a corollary, sometimes you don't have the H plus concentration, sometimes you have the hydroxide concentration. And if you have the hydroxide concentration, you can solve for what's called the POH, right? It's the negative logarithmic of the hydroxide concentration. It's the same thing. So by that logic, you can find the POH, and you could also find the hydroxide concentration if you have the POH, right? So this is useful because if you understand the concept of Kw and how Kw is 1 times 10 to the minus 14th, really what that is this is the concentration of H plus and OH minus for water at equilibrium. Therefore, if I know one of them, if I knew this, I could find the other. Now, I could simplify this equation, and I could just take the negative log of both sides, and if I do, I get this. Because the negative log of 1 times 10 to the negative 14th is 14. And this is going to be a time saver because this will allow you to convert any measurement you have about an acid or base into something useful. Right? So imagine I ask you, well, here. We know the pH of blood is approximately 7.4, and for some reason I only have one decimal place there, so I'm going to artificially add a 0. Suppose the pH of blood is 7.40. Find the other values using the equations. How can I find pOH? Let's start with that. Well, what is if we know pH plus pOH is 14, and if I know the pH, pOH is simply 14 minus pH, right? So the pOH is equal to 6.60. Make sense? Okay, so now I have pH and pOH. Now I can very easily find H plus and OH minus. So hydroxide ion concentration, you should get 2.5 times 10 to the minus 7 molar. And then for the H plus concentration, should get, we're going to have to round this, 4.0 times 10 to the minus 8th molar H plus. All right, are you guys with me? Everybody understand how I got those? As long as you know one value for any acid or base solution, you can find all of the others using these equations, okay? Okay. Then tell me what is the pH if I have a solution of sodium hydroxide that is 0.15 molar. All right, sodium hydroxide, 0.15 molar. What's our pH, guys?
13.9.
Yes. First of all, ask yourself a common sense question. Is this an acid or a base? It's a base. Do you expect the pH to be above or below 7? Above. This is a strong base. That means far above 7, right? So the first thing you do is you must realize that 0.15 molar sodium hydroxide, it's a strong base, therefore your concentration of hydroxide is 0.15 molar. And then you negative log that to get your pOH, which will subtract from 14 to get your pH, and that's how we end up with 13.18. Because initially you might have gotten 0.82 and said, what? That's a really low pH for a base. Well, of course you have to subtract from 14. Okay. And these are just more examples of solving for whether something is an acidic or basic solution. The key idea here being that in water, you have dissociation, which produces H plus and OH minus, right? Why is water neutral? If water is acidic, it's acidic because it makes H plus right here. I see it right there. Why is water considered neutral? Is H plus the only thing made when water breaks apart? No, it makes hydroxide in equal amounts. So you actually have both of these present in equal amounts. So if Kw is equal to the product of both of these, then I can set up this expression right here. X being the concentration of H plus or OH minus. So X would be 1 times 10 to the minus 7. So that's the concentration of H plus and OH minus in water. So what happens if you take the negative log of 1 times 10 to the minus 7? What do you get? 7. That's why we consider a pH of 7 neutral. I could take the negative log of the OH minus concentration. What do I get if I did that?
You also get 7.
Still 7. Okay. So another way to gauge if something is an acid or base is to just look at the H plus concentration and see, is the H plus concentration greater or less than 1 times 10 to the negative 7? Right? And that kind of would also tell you if it's acidic or basic. Or you can just take the negative log of it and figure it out via pH. Either which way. Okay. This is a good stopping point here.